Imagine this ruler as a reinforced concrete beam. When load is applied, the top portion is in compression and bottom portion is in tension. Did you know that concrete is strong in compression and weak in tension? That is the reason we use reinforcing bars inside concrete. When steel bars are needed only in tension side of the beam, we call it as singly reinforced concrete beam. In today's lecture, I will cover second example related to singly reinforced concrete beams as per Eurocode 2. Click on this side of the screen to watch other examples and theoretical background related to singly reinforced concrete beams. Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer in structural engineering and design at University of East London. On this channel, we explore civil engineering and human skills to help us lead more productive, happy, and examine life. I'm going to solve one tutorial here, example, which is related to design of singly reinforced concrete beams. We have a simply supported reinforced concrete beam that is shown in this figure. Both permanent and variable loading is as indicated. Assume FCK 25 Newton per millimeter square, FYK 500 Newton per millimeter square, and we have to calculate the moment of resistance for the reinforced concrete beam. Moment of resistance means that we have to work out MR. Now what it is asking us that should this beam be designed as singly or doubly reinforced? If moment of resistance is greater than MED, then we will say that this is singly reinforced. If MRD is less than MED, then this will be doubly reinforced. So we simply have to tell that if it should be designed as singly or doubly reinforced. And secondly, determine the area of main steel required for the beam and suggest a suitable size and number of bars. Now what is asking is, it is asking area of main steel required for the beam. Now if it is singly reinforced, main steel will just be AS1 or tension steel. If it is doubly reinforced, then steel is going to be main tension steel and compression steel. And determine the suitable number of bars, size and number of bars. And then finally draw the simplified stress block for the beam, making all relevant dimensions and force values. The section size is given to us, which is 300 by, the overall depth is not given, the effective depth on the other hand is given, which is 500 millimeter. And GK is 5 kilonewton per meter, QK is 10 kilonewton per meter, span of the beam is 8 meter. So let me move on to the solution. The section size is given to us, D is given to us, FCK is given to us, FYK is given to us. So the first thing first, we will work out the total design load. And design load is 1.35 times GK plus 1.5 times QK. So QK and GK, they are given, and then you work out the design load, the ultimate load, and then you work out the design moment or applied moment. So applied moment will be equal to WL square over 8 because we have UDL. If we had a central point load, then moment is going to be PL over 4, applied load over 4. If we had combination of central and uniformly distributed load, central point load and uniformly distributed load, then we will add these two moments up. So WL square over 8, W is your design load, which we worked out here, and 8 is your span, which is 8 meters. When you work this out, it comes out to be 174 kilonewton meter. Now have a look at marking scheme as well. So if you work out design load, you get 2 marks. It's not going to be the same, but similar. And then if you work out design moment, see the steps, you're getting 3 marks. Yeah. Then we have to work out ultimate moment of resistance or moment of resistance of the beam. Now simply, I am trying to follow these steps here. Up to this point where you find out ultimate moment and decide if it is singly or doubly reinforced beam, the procedure is same. Beyond this point, where the MRD is greater or less than MED, then you decide if it is singly or doubly reinforced beam, and then you apply appropriate formula to that. Now next step is to find out MRD, and you don't have to remember this formula, it's given to you.
So 0.167 FCK is compressive strength, B is width of the beam, D is effective depth of the beam. Both B and D, they are given to us. So B is 300, D is 500. So when you enter those values, you have 0.167 into 25 into 300 into. Now remember that D has got a square. This is one of the common mistake that students have been committing over the years, is that sometimes they forget to square it. Then suddenly, it changes the answer. So D has got a square, and then the resulting value that you will get will be in Newton into millimeter. Don't forget to convert it into kilonewton into meter by dividing it by 10 raised 6 or multiplying it with 10 raised minus 6. This is absolutely crucial that you convert it into kilonewton into meter. Otherwise, you're always going to design it as a singly reinforced concrete beam, which may not be the case. It means that if you make a mistake here, then your entire procedure is going to be incorrect and you will lose lots of marks. If you work out MRD correctly, then the rest is fine. So some of the students, they would purposefully make it singly reinforced concrete beam so that they can follow the easier process. But trust me, you lose lots of marks for that. And this is absolutely crucial that you convert it into kilonewton into meter. In fact, I shouldn't be talking about losing marks. I should be saying that you will gain 100% marks. I'm not the one who will talk about losing. So, so you will gain lots of marks if you do this step correctly. And then after that, you can pretty much get 100% marks if you do this step correctly. And then rest is a kind of recipe. Now, how do you check that if your MRD is fine or not? So for example, if you are getting 6-figure value over here for MRD, it means that you probably have made a mistake and it can't be compared with this MED 174. So the values should actually be a little bit comparable. They can't be really very high value for MRD. Now you can see clearly that MRD is 313 kilonewton meter and MED is 174. So MRD is greater than MED. So design as singly reinforced. Only for this step, you can see that you're getting 2 marks. So don't simply leave that step. Because it's asking you, should it be designed as singly or doubly reinforced beam? You should tell that, okay, yes, it should be designed as singly reinforced beam. Now, once you have established it to be designed as singly reinforced beam, then you follow this process. So first of all, you will find out K0 and then Z and then AS1. Any question up to this point?
Yeah, Jawed.
Yes, Teddy.
Will the force, the loading on top, always be UDL?
No, that's what I said earlier. If it is a point load, then you use PL over 4.
Okay.
I mentioned it over here. So the loading can be central point load L over 2, L over 2. So for central point load, your MED will be equal to PL over 4. You can have combination of uniformly distributed and central point load. In this case, your MED will be equal to WL square over 8 plus PL over 4. Or you could have off-center point load. So for example, if you have off-center point load, this distance is A, this distance is B, and this distance is L. So your reaction here at A and B will be equal to load multiplied by off span. P is off span divided by full span, and your reaction here will be load multiplied by off span is A divided by full span, and your moment is going to be M is going to be PAB divided by L. So you could have a combination of different things. Okay, thanks for this, Teddy.
Thank you.
Once you have established it has to be designed as singly reinforced concrete beam, then the rest is a kind of a recipe. So then you have to follow these steps. So K0 is equal to MED over FCK BD square. Remember that FCK is related to concrete. It's concrete compressive strength, and FYK is related to steel. It is yield strength of steel reinforcement or reinforcing bar. Now MED is applied moment, which is 174 here, and FCK is concrete compressive strength, which is 25. This can be different. It could be 30, it could be 35. B is width of the section, which is 300, and D is the depth of the section. And do not forget that there is a square on D. And then from here you work out value of K naught as 0.098. The next step for me is to work out lever arm, which is Z. This lever arm is equal to D into 0.5 plus under root 0.5 minus 3 K naught over 3.4, where K naught has already been determined. Now, if you put all these values here, 0.0928 for K naught, and if you put value of D here, okay, now D is given here. Sometimes D is not given in exams and you have to work out using the same procedure as I mentioned in the lecture, okay? Sometimes overall depth is given, which is H. Now this will give you value of Z. Now Z is 455 millimeter. Now finding area of steel, again formula is MED over 0.87 FYK into Z. MED is applied moment, which is 174. Don't forget to convert it into millimeter and newtons, because in the denominator you have millimeter and newtons. Putting value for FIK 500, putting value for Z 455, you get value of area of steel as 279 millimeters square. Now once you have it, then you go to this table and you can simply choose pretty much anything. So for 879, you can use these 3 H20 bars, or you could use 2 H25 bars. So it's entirely up to you what you use for it. Let us see what is done over here. Now provide 3 H20. 3 H20 means that it will give you 943 millimeters square. And then draw a sketch like this. These are 2 parts, A and B. Part C has got 5 marks. So do not leave this part C. Now here you have to draw this S, where S is equal to 0.8x, FCD is equal to 0.85, FCK divided by 1.5. X is equal to, now first of all draw this diagram and then draw this stress diagram, all right? You have Fs, which is the force in steel, and then you have Fc, which is force in concrete, and this is the concrete block. Because this is a stress diagram, it is only showing you depth, okay? In the horizontal dimension, it is showing you stress. So you can't work out area like Fs times FCD. So that's the reason you work out area by multiplying this S with the width of the section, because this is effective up to this point. So first thing first, you will find out value of X. X is distance from the neutral axis to the top fiber, and this is usually 0.45 of D. All right, this is something that I think you will have to remember. I think 0.45 D, and where D is given, which is 500. So when you determine this, it comes out to be 225. So then you write the value of X. Now once you have got these values, then you find out value of S, where S is the depth of the concrete block. So depth of concrete block is normally 80% of X. So 0.8 times X is determined earlier, which is 225. S comes out to be 180 millimeter. Any question up to this point?
Yeah, I just don't understand the way the diagram is shown.
The way the diagram is drawn.
Yeah.
The way the diagram is drawn is, this is the stress block. This is neutral axis, and this is B, this is D. From flexural formula, from level 4, stress is equal to My over I. So where Y for a homogeneous section is normally equal to D over 2. In our case, it's X. Y is equal to D over 2 for a homogeneous material where you just have steel material or anything which is made up of one material. Or you could say that Y or X is 0.5 D.
Yeah.
Then we determine this from this flexural formula. So flexural formula, and M is your applied moment and Y is your distance. This is elastic range. So normally you would get value of stress, high value at the end. When you reduce this Y, you will get a smaller value. And in that way, you will get something like this. So the top portion is compression and bottom portion is tension. So this is the elastic stress distribution. On the other hand, if you have plastic stress distribution, so if I wanted to draw it for concrete in the elastic range, the tensile stress of concrete is nothing, means I will discard that. Yes or no?
Yeah.
So if I wanted to draw the plastic one, completely plastic, and that diagram will be like this. It means that material goes into plastic range. If I talk about steel or any material which shows some plasticity, that will be drawn like this. So these are two extreme. Now this is a typical one for steel, but for steel, it is strong in compression, it is strong in tension as well. So I can draw it like this. So for concrete, if I'm talking about plasticity, certainly I can say that for tension, I just have steel reinforcement. So I will just have one force in the bar. Except this bit, I have nothing. There's no stress. Other portion of the beam is not taking any stress. Only steel is taking tension stress. Yes?
Yeah.
I will just have this line which reinforcement will take care of. Then I have this block. Research has shown that something which is near to the neutral axis, concrete cannot take plastic stress. So concrete can take only stress up to this point, which is S. So this portion is not contributing to compressive stress. And again, this is the idealized stress block for concrete. This is force in compression, and here in steel you will have force in tension. And this is design concrete strength. So these are your stress blocks. Now if you ask me what is the area of this stress block, what area of the section is contributing, I would say its depth is S, but width is not shown here. Stress is shown on the other hand. So I would simply go here and then I will say that this is S and this is B. So if I wanted force FC, that will be stress times area. So stress is FCD, area is B times S. Does it make sense?
Yeah. Cheers.
Could you please go over the last part of the diagram? Yes.
Yeah. The last part of the diagram is the research has shown that when you conduct experiment on a reinforced concrete beam, then its stress block is normally like this actually. But we idealize it to the one that you see on the left. So we idealize this block as this one for design purposes. We say that this part is taking compressive stress. All other thing is not taking any loading. This part above neutral axis, this is not taking any loading. And this is shown in research. And after that, the design codes, they have developed the formula. The tensile side is not taking any, it's not contributing to the load. So only steel reinforcement is contributing to the load carrying capacity. The FT is balanced by FC. Now, if you wanted what force is this, then you want the area on which this force is acting, which is this, B and S, and then you multiply it with the stress, which is FCD. This will give you force. Now, if you wanted force at the bottom on the tension side, because concrete's strength in tension is 10% of compressive strength, and even that 10% is ignored in the design. So that's why we don't have anything under neutral axis. And if you wanted FT, certainly force is always equal to area times stress. Area, and F in our case is FSD. We're using the design one, all right? FYK is given, so we use the design strength of steel. The reason is that because we're using codes. And area is simply area of tension steel. But because we're not using the elastic one, our modern design codes are based on the limit state design or ultimate limit state design. So that's why we're not using the elastic theory. Instead, we're using this plastic one, but because concrete, it has got negligible strength and tension, so this portion is ignored. And then only steel is contributing on the tension side. The area above this 20%, the depth, this is not contributing. This is 0.2x, and S is equal to 0.8x. Does it make sense?
Thank you so much, Jawed, for breaking down the diagram. It finally makes sense.
Yes. A lot of research goes into development of the design codes. And certainly what we're using here is FCD. It means we have multiplied lots of factors. And FSD as well, we have multiplied factors. But in reality, when you work out experiments, you get the experimental value. We carry out lots of experiments. So for example, 10 experiments, and we work out these factors from that. So that takes into account the effects of any variability in testing. So certainly, if you test one specimen, there could be 10% difference between testing 3 specimens, to be honest, and I have seen that myself. So to take into account effect of those variabilities, we come up with these characteristic values and design values. So coming back here, we have this stress diagram in which you can see that the concrete is only resisting this part where its depth is S and its width is 300. And FCD is design stress in concrete. So S is the depth of this stress block. Again, how do we say that it is 0.8x? Again, after conducting a lot of experiments, we have determined that for rectangular sections, it is 0.8x. And X, on the other hand, is 0.45D. Normally, if the section is of one material, homogeneous material, then this is the centroidal axis. Normally, it is 0.5D or half D divided by 2, as you saw earlier over here. But because this is reinforced concrete, that's the reason it is a heterogeneous material. So again, by doing lots of calculations, it comes out to be normally 0.45 times D. Now, once we have S and X, we're ready to work out FC, force in concrete. If you had compression reinforcement, then definitely you will work out force in compression reinforcement as well. But here, force is equal to stress times area. The stress which this compressive block is taking is this design stress, which is taking into account various factors. So FCD is equal to 0.85 FCK divided by 1.5. Again, these are safety factors. So if you put the FCK 25, you're getting 14.17, which is FCD. So putting FCD over here, S we already determined, and B is width of the concrete. So we are dealing with this area. This is S and this is B. That is contributing to force in concrete. And in that way, you get force in concrete, which is 765. Then you work out Fs. Fyk is 500 and divided by 1.15 is a factor. And then you multiply it with AS1. Actually, it should be this area, 879. 879 times 500 divided by 1.15, 382. So Fs will give you 382 kilonewton.
But we have to use the provided area, right?
We have to use the required area, not provided one. So which is 879.
So that was wrong?
Yeah, this is wrong. Yes. Now here, interestingly, you would say that earlier when you showed us that forces in compression and forces in tension, they are in equilibrium, they are equal, then forces in concrete and forces in steel, why they are not equal. So I will leave you to think about it, and then I will talk about it probably next week or so. Any question?
Could you maybe give a hint?
Yes, the hint is because you can see that this moment of resistance 313, this is quite high, almost double as compared to applied moment. If this was closer to applied moment, then the force will be same. So this means that the concrete part is quite strong as compared to tensile part.
Does it mean that the concrete part is over-designed?
Yes, it's a very good guess. It's over-designed. Yes. We could reduce the size of that part. So I will leave you to solve this another question. The first part A and B of this question, they are pretty much same as the first question which I did. So I will ask you to solve this question yourself. Part C is after the design has been completed, the client wishes to limit the width of the beam to 200 due to architectural considerations. What effect would this have on initial design? Immediately think about it. Tell me what effect would it have if B is reduced?
I mean, it'll probably reduce the moment resistance.
Excellent, wonderful. So it will reduce the moment resistance. So to respond to this question, simply you would say it will reduce if the width of the beam is limited to 200, then the moment resistance will be affected, and the revised moment resistance will be 0.167 FCK BD square. So if you put 200 instead of 300, then you can see that the moment resistance is 133. So the revised moment resistance is 133, which is less than applied moment now, because previously with 300, B equal to 300, your moment capacity, ultimate moment of resistance of the section was 200, which was higher than applied moment. It means that we could design it as singly reinforced beam. But now, because moment resistance is less than applied moment, therefore the beam should now be designed as a doubly reinforced beam.
Thanks for watching. Don't forget to subscribe for more practical insights into structural engineering and beyond. Until next time, stay curious.